Good morning, ladies and gentlemen. I'm J.V. Venable, Senior Fellow at the Mitchell Institute for Aerospace Studies, and welcome to Aerospace Nation. For decades, the U.S. has enjoyed an unrivaled position in fielding high-performance, reliable military jet engines. However, today, the U.S. Air Force is at a key inflection point when it comes to jet propulsion. Most of the service aircraft are flying with engines designed during the Cold War. The few designs that were fielded in the years beyond are now decades old. This is why the Air Force has invested in programs to pursue new engines to deliver greater performance, reliability, and efficiency that will meet future mission requirements. But the service can't manifest innovation alone. The aircraft propulsion ecosystem is incredibly complex, and it takes a healthy government-industry partnership to manifest the results needed to maintain an air combat advantage. Today, we're going to learn more just about where military propulsion stands and where it's headed in the future. That's because we've got this strikingly handsome man next to me, is Steve Doogie Russell. He is the Vice President and General Manager of GE Aerospace at Edison Works, and he's one of our nation's top propulsion experts. Doogie, thanks so much for being with us.
I appreciate it, JB. Appreciate the invite to be here. And I do think this is a topic that probably doesn't get the level of attention it deserves given its impact to our warfighters.
I think it's about time we amp that up, don't you think?
Amen.
Also joining us in this conversation is our own Heather Lucky Penny. Heather, thanks for being here.
It's a pleasure to be here. Thank you, JV.
Before we begin our conversation, Doogie, if you would, please give us a rundown of how you see the state of military aircraft propulsion today.
Yeah, sure, I'd be happy to. And I'll start with sort of the broader industry look and then talk a little bit about GE Aerospace specifically. So as you point out in your opening remarks, for decades now, the United States has developed and delivered the highest performing, highest reliability engines anywhere on the planet. So the short answer to your question is today we have a distinct asymmetric advantage over our adversaries when it comes to the propulsion area of our threat environment. The challenge, however, and this is a big however, is that that advantage is not really guaranteed for the future. And we know that our adversaries are closing the gap. They're getting better and they're getting closer and closer to the performance we deliver on our legacy engines. And so if there's one point that I hope everybody takes away from our discussion today, if they don't tune in for the whole time, or it would be that it's absolutely crucial that we continue to invest in these next generation programs that are developing that next generation of propulsion technology, whether it's F-47, FAXX, or the next generation adaptive propulsion or NGAP program. Those are absolutely essential if we're going to have that same advantage for our future warfighters that we have for our warfighters today. So that's kind of a big industry look at it. If I talk about GE Aerospace specifically, we're very proud that for over 100 years we've been teaming to provide that advantage to the United States military and to our allies. If you go back even to the very first operational jet fighter, the P-80, that had a GE Aerospace engine in it. We weren't called GE Aerospace at the time, but it was a GE Aerospace engine. The first Mach 2 fighter, the F-104, that was powered by GE Aerospace. The F-117 for stealth fighter, B-2 for stealth bomber. So we've got a long history of delivering this capability to our nation and our allies. Fast forward to today, so we power 2 out of every 3 combat aircraft that are in the U.S. Air Force's inventory, and a number of our allies, combat aircraft as well. And so we at Edison Works now are focused on what does the future look like. And there's 3 main thrusts that we're focused on in the future. The first is adaptive cycle engines. I'm sure we're going to talk more about that in a minute, but those very rarely in the propulsion industry do you get the opportunity to provide a generational leap in performance, and adaptive cycle can do that. The second area is hypersonics, both for weapons and for aircraft. We probably won't dive as deep into that today. But then something that's the complete opposite end of the spectrum is we have a real focus on low-cost, small engines for uncrewed applications, so like cruise missiles, right. Collaborative combat aircraft. And it's a completely different thought process to develop an engine that's only going to operate for a few hours or a couple hundred hours, as opposed to one that needs to operate at a high performance for thousands and thousands of hours. So in my very long answer to your very short question, today we've got a pretty distinct asymmetric advantage, but it's not guaranteed for the future. We have to invest if we're going to be able to have that in the future as well.
Oh, I love the response. It leads into my next question. We kind of have a bifurcated series of platforms and engines in the United States Air Force. Some, like the jets, the engines that Heather and I flew, are decades old. And then you have new designs that are coming out. You mentioned NGAP, the next generation air propulsion platform. What are the challenges and opportunities that you see now as a partner in this industry world?
Yeah, so I think you bring up a good point, is that we're simultaneously producing the highest performing jet engines on the planet today, but we're also developing the next generation of technologies. And so I'll start with opportunity. One of the great opportunities that brings is, as we're developing those new technologies, we can actually feed them back into the legacy engines that we have. I smile to myself when I say legacy, because one of my colleagues hates it when I call today's engines, which are the highest performing in the world, legacy. So Sean Warren, that one's for you, but I've got the mic, so I'm going to call them legacy. We're feeding new technologies into those. So a perfect example is the F-110. So the F-110 went into production in 1984. It's over 40 years old. But today the F-110, for those that aren't tracking it, is actually the chosen engine for the F-15EX, our most modern fourth generation platform. It's on the Saudi F-15s, it's on the Qatari F-15s, it's on many variants of F-16s, both in the US and across our allied nations. And today's F-110 is not your grandfather's F-110. It's completely changed. 92% of the parts that were in the original F-110 have been upgraded during the lifetime of that engine. So it's definitely not the same one that you had there. So we're able to take these advanced technologies that we're developing and feed them back into our existing engines to enhance their performance there. On the challenge side of things, though, one of the biggest challenges that we have in the industry, and I'm sure I'm going to hit this a number of times, is that we're not getting a consistent demand signal when it comes to the need for these next generation engines and next generation platforms. If you think about the ups and downs we've been through over the past year, we start our industrial base, we start our supply base, we spool them up to go, and then if you get a pause or you get a signal that says we're not sure what's going to happen, we have to spool everybody back down. And the skill set that's required in this environment is not easy to replace. So if you lose your people, if you lose your supply base, it's very hard to ramp them back up, and it doesn't happen quickly.
I'm going to take that and sort of flip the script a little bit, because Doogie, you talked about how innovation feeds the legacy engines, but I think it's also really important to understand how operationalizing engines, so buying them, fielding them, and having them in aircraft and at units and in that operational environment is really crucial towards developing that next generation of engines, because you don't know what you don't know when it comes to how the pilots are actually going to operate them. So there are certain things, for example, that we could not anticipate. If you take a look at the F-35, we didn't expect that the engine was going to be so high performing that it'd make glass in the desert environment, right? And so there were things that we learned through the operationalizing, the fielding, that drove sustainment, and that sustainment then feeds back into that innovation cycle. So it's not just pursuing those advanced technologies that are crucial that feed back into legacy engines. It's about actually fielding the engines that we have and fielding that next generation of engines in order to be able to maintain that innovation cycle.
Yeah, so we were talking before about Heather flying at the DC National Guard, the small mouth GE-110. I flew the big mouth GE-110 at Torrejon, Spain, and the thrust was just amazing, comparatively speaking, to the previous platforms that I had flown. But what you're saying now is that engine, as old as it is, has been upgraded over time, and it is more reliable, produces better thrust. Go on with that.
Yeah, that's exactly right. So the engine that's in the current F-15EX, for example, today is higher performing than the engines that you flew just a few years ago. And part of that is because there's this constant upgrade cycle. Yeah. And as we're advancing material technologies, as we're advancing our ability to, I'll talk later about hot parts in the center of the hot engine, but the more you can crank up the temperature, the more you can crank up the performance, and we feed that into our existing engines that are in production.
Yeah. How do those feed into existing engines as they go through their phases and inspections? Are you able to upgrade of engines that have already been fielded and installed?
You can, but there's a process that you have to go through. So the way it normally works is we'll feed the technology back into our industrial base. They'll go through the qualification program, and then it will be fielded and then flow back out.
Excellent.
Yeah, so on the innovation side of the equation, you've got NGAP coming on board as that propulsion journey continues. Could you talk a little bit about the evolving requirements and how the government is looking at that engine?
Sure. So NGAP, Next Generation Adaptive Propulsion Program, I can't say a lot about the program specifically, but I can talk more generally about where we're going. I mentioned in my opening remarks that it's not very often that you get the opportunity to offer a generational leap in performance. So in the propulsion industry, if you can add an efficiency gain of 1 or 2%, that's pretty significant. Particularly on the commercial side, that's millions and millions of dollars in fuel savings for the commercial side. For the warfighters, that's range. Every little bit you get gives you some additional range or some power that you can pull off the engine to run other things. So An adaptive cycle engine is different than today's modern turbofan. So if you think about the F-110, it's a turbofan engine. I won't geek out too much on you, but it basically has two streams of airflow that are coming through it. There's one stream that goes through the core of the engine. So that's the stream that gets compressed, mixed with fuel, it ignites, and then provides the maximum amount of thrust through the back. But it's not a hugely fuel efficient process because you're putting a lot of fuel in there. So the second stream of air goes on the outside of the fan, and you can think of it almost like a propeller in the front of the fan is feeding that stream. That's a much more fuel efficient way to deliver thrust. But that bypass ratio between the internal stream and the external stream is set. So when you design your engine for whatever platform, that's going to be set, and that's essentially the fuel efficiency you're going to get depending on what part of the profile you're in. The way an adaptive cycle engine works is there really are actually three streams of airflow. So you've got that one through the core we talked about, you've got the one on the outside to provide thrust from the fan, but then you also have a third stream that can be pulled off to cool the systems that are on the aircraft. So modern systems, you were talking about F-35 and F-22 earlier, those systems require a lot of cooling because they run hot. There's a lot of RF systems in there that burn electricity, and so this third stream actually benefits the platform in other ways. But back to the efficiency of these approaches on the adaptive cycle. So you can, in real time, change the amount of air that's flowing through the different streams. So rather than it being set like it is in today's turbofan, by changing the ratio of what air is going to where during different phases of flight, you can be much, much more fuel efficient. And so now I can jump into the actual program. So the precursor to the NGAP program was called the Adaptive Engine Transition Program, AETP. And in that program, our offering was called the XA100. So we built two engines. We ground tested them for over 400 hours. So showed the performance, but the performance that was demonstrated was about a 25% increase in fuel efficiency, which would translate to a 30% increase in range for our warfighters. So that's a huge leap. That's not the 1 or 2% that we're talking about with the current generation of improvements. It's a huge leap in performance that we could offer our warfighters. And so what the NGAP program, unfortunately the XA100 program and our competitors program, the Air Force decided not to go forward with fielding them. It was sized for the F-35. And since they didn't decide to do that, the Air Force Lifecycle Management Center, the propulsion directorate specifically, and to their credit, they recognized that all of this expertise that we built up on adaptive cycle engines needs to be continued. And so the NGAP program was stood up as a follow-on to make sure we continue to advance that technology and make sure that it is available for our warfighters in the future when it's needed.
I want to jump in here, Doogie, because I think it's really important to emphasize how crucial that adaptive engine technology is, because being able to change that the ratio really provides resilience to the thrust of the engine, because those high bypass engines, like what we see on commercial aircraft, that's why those engines are so huge. They're really set, and you don't move that. You get to cruise and you set it, and that's it. But in a tactical aircraft, you're constantly changing the throttle, and your angle of attack is going to be changing. So the amount of air going ingested into the engine is going to change. And the engine has to be able to adapt to that so you have a smooth engine flow. So you don't have compressor stalls, which can destroy the engine. You don't throw a fan blade or things like that. And that's really important for our warfighters to be able to rely on their engines. We don't want them to have to think about, how do I manage my engine and baby that when they're in a tactical environment? And so that's really crucial. And I'm glad that the engine program office chose to retain the talent in place and continue to develop that, because we didn't buy those engines. And if you don't buy them, the engineering team, you have to disperse that, because you're a business, right? You've got to ensure that you're employing your teams, you're employing your engineers, you're employing your workforce appropriately. And so if you don't maintain that team together, you lose all of that intellectual capital.
Yeah, that's a great point.
I just love the AETP, the entire program, because if you ask for more thrust, you can get it by throwing more gasoline in there and turning up the temperature, right? But if you want more thrust, more range, a greater heat sink, and then more engine durability, if you want all four of those are four consecutive miracles coming together, and that X100 engine delivered all of that. In that process, in the process of going through this discovery, what's been your biggest surprise?
Yeah, so I'll go one tied to XA100, then I'll kind of go on a tangent for you, but there's a reason, I'll tell you why. But so on the XA100, like one of the big takeaways I have from there too is we talked about controlling these different streams, it'll flow going everywhere. a huge challenge that the team overcame on that one was just what's the control system that does that in real time and that is reliable. So it senses where does the pilot want to go, what thrust do I need to demand, how do I automatically adapt the different streams that are coming through. It's a really complex control system. So it's beyond just the technology that goes into the parts and the design of the engine, but that control system is a really big part of it. And again, maintaining the talent pool that knows how to do that was critically important. I think the other big surprise for me, just in general in the propulsion industry, is if I go put my old Air Force hat on. So I retired in 2017, but I was running around the Pentagon in the 2014 timeframe, and we were working on what ultimately became the Aerospace Innovation Initiative. And so we were talking to a number of folks in the building. We were laying out, hey, if we're going to do some demonstrations to buy down risk for future platforms, what would a 6th-gen platform program look like? What would a 6th-gen engine development program look like? And as that information came together, what was striking to me is that, and I hadn't realized this before, is that it actually takes longer to develop the propulsion system than it takes to develop the platform. And that was shocking to me at the time. I guess now, knowing what I know now, it shouldn't have been. But everybody we briefed all the way up the chain, it was shocking to them as well. And I think what I had in my head prior to that was that these engines are just sitting on the shelf somewhere, and when I want a next-gen platform, I go pick that one. If I want this type of platform, I go pick that one. When the exact opposite is true. You actually have to be investing in the engine technology first, even before you know what your next platform is going to look like. And so that has really stuck with me over time. And I don't know if that was just me or if that's a commonly held misbelief, but I think we take it for granted that the propulsion systems are going to be there when we need them, but it takes deliberate action to actually develop them.
Well, I think we take it for granted because it's been a really long time since we've actually developed new aircraft and new engines, right? I mean, really the last time we did that was with the F-22 and the F-35, but the F-35, that engine was a derivative from the F-22's engine, which was, again, another series of consecutive miracles to be able to do that. But if you look at everything from the Navy's Tomcat, the F-14 in the 1970s, the Eagle in the 1970s, and you go back to the Century series, what we found was to get that next generation level of performance of the airframe, we had to have a next generation engine, and the engine always lagged. And so the aircraft and the big program itself ended up being vilified for being past schedule and over budget and all of those things, when it really was about planning and not anticipating that we'd need to develop the engine early in order to be able to get the performance that we need. And it's more crucial now because with a swap C size, weight, power and cooling, that's a physical property that comes from the engine. It's nearly entirely derived from the engine, and you have to design that in early. So we saw that, for example, in the F-22, where we had all of this processing, all these incredible sensors, and it delivered incredible capability to the pilots, but we designed it for 50, 60,000 feet, not necessarily sitting on the ramp at Georgia waiting to get your clearance, or in the desert, or in the Southwest, the Pacific. And so overheating on the ground became a real issue. So we need the engines to be able to provide that kind of cooling, the power, the electricity across all regimes, whether or not that's sitting on the ground or whether or not that's in the tactical battle space environment. And so that's something that is going to additionally burden the engines, and we have to think about that and design for that. And that's exactly what our companies are doing now.
Yeah, I'm going to spin on that just a little bit, Heather. The XA100 was designed to go into the engine bay of the F-35, be a fit. If you change that design, let's say you want a bigger engine or a smaller engine, is the developmental timeline the same?
Yeah, the short answer is it depends, right? So if you're building an entirely new design, developmental timeline is still the long development timeline for the engine. However, what you can do in a lot of cases is take the core of that engine, put a different fan on the front, and you can resize it, to fit into different platforms. And in that case, it's a much shorter development timeline. There's still, you have to go through, the actual design and the qualification, but it's not the 4 to 5 year timeline that you would normally think about a new engine development. So it depends on how you want to use it and how much of a change it will be.
Very, very good. So we've talked a little bit about AI, and I've spelled it 3 times correctly today. I just want to brag a little bit. I know that's got to help with data consumption and investigation on the streams that are coming off of the engine in the test world. Could you talk about how it's being used in other aspects of engine design and development?
Sure. So at a high level, we have a couple of different initiatives going on related to AI. So we have decades and decades of performance data on our legacy engines. I'll say that for Sean again, who might be watching. So what we're able to do is take that information, ingest it into a large language model, and then use AI to then do predictive type of activities for fleet management. So we're partnered with Palantir right now, who a lot of people are partnered with Palantir, but using some of their capabilities to then do a pilot program for the Air Force where we take all that data in, and then you can make predictions of, hey, when is a part going to be needed over in this part of the country, and you can preemptively get the part over to that location. So that's one use of it. The second one is more on the Edison Works side of things. Is as we look at trying to shorten our design cycles, there is an opportunity. We've got, again, decades and decades of design data on high performance engines, and you could ingest that into your models, and then you could potentially turn around your preliminary design cycles, whether it's for a part or for a subsystem. The challenge on both of these initiatives that I pointed out, though, is that a lot of that data that I'm talking about is not in a mode that's easily ingestible into a model. It's not like it was all set up as data that's digital and tagged ahead of time. So there's a huge amount of effort that goes into just getting the data into the environment so that the large language model can actually learn on it.
The blade temperatures, the different areas of the core. I cannot imagine how many signals and data streams are coming off of the engines as we go. So adaptive engines are one side of your world, but in the Cincinnati plant, you guys have additive manufacturing. Now, as a skeptic, fighter pilot, knuckle dragging as I am, I went down to Cincinnati thinking it wasn't going to be anything special, and then my eyes were rolled back in the back of my head. Unbelievable what you're doing. Could you talk about how that's maybe even surprised you?
Yeah, so there's a couple of thrusts tied to additive that I think are particularly beneficial.
No pun intended
yeah,
there, right?
Right,
Like
well,
that.
yeah, thanks. Yeah, you see how I did that? Yeah. So on one hand, the additive allows you to do rapid prototyping. So we certainly are interested in doing that type of work. I talked about low-cost small engines. So if they don't need the same level of performance necessarily that you would have for a really high-performance engine, there's an opportunity there to potentially use additive to very rapidly go through iterations of your design and actually build them and demonstrate them. Our hypersonics team, we're probably not going to talk a lot about hypersonics, but those folks have printed entire nozzles, that run our ramjets with additive technology, and they can do that quickly. And so in their case, they can go from a concept to actually firing the engine on the ground in 11 months, which for people that work in the classic turbo machinery world, that's things that you just don't hear about. And we've done that 3 times in the last 3 years, where they've built a different hypersonic ramjet and they run it from concept to delivery in less than 11 months.
Now, I have to say that that's really impressive, because when you talk about using additive manufacturing for small engines, like what you would use for a rocket or a weapon or a CCA, you go, well, we can accept some manufacturing flaws, some quality flaws in there. But if you're doing hypersonics with that really demonstrates a real mastery of the materials as you're doing the 3D printing, because the granular structure, that really matters at the molecular level to be able to get that kind of level of performance and to do so reliably and safely.
That's exactly right. So the state of technology has advanced dramatically from where it was just a few years ago. I think another area we're using it now. You mentioned earlier that when you talk about swap C, the P and the C, the power and the cooling, are taking a huge, a even more important part of the equation. In the past, there was more focus on S&W than there was on the power and the cooling. So something we're doing with additive is you can design structures that you just can't manufacture with a traditional manufacturing method. So when it comes to cooling, you can put really tiny veins where air can flow through even a tiny part. But if you're building it up individually, you can have hundreds of those veins flowing through. That could be cooling air that cools the part in real time. And so we've seen that in parts that are inside the engine, also in heat exchangers that take heat out of the air, and then that air flows or other places to cool. So there's a lot of opportunity on the additive side right now, and we're continuing to work on it.
Very cool. So we have talked quite a bit about U.S. demands, specifically U.S. Air Force demands for engines. What's it looking like on the international scene? Any different perspective? What are they thinking?
I would just say that given the threat environment, there's significant increase in demand in the international stage as well. I mentioned the F-110 is on both the Saudi F-15s, the Qatari F-15s, a huge number of F-16 variants across our allies, and we're actually seeing that demand continue to grow because they need high-performing platforms to address the threat environment just like we do. I think an interesting trend on the international front, though, is particularly when you look at the European theater, a lot of our European allies are starting to catch the interest in the collaborative combat aircraft as well. You know, the Air Force is a little farther along on our concepts, where we think we want to go, how we're going to use them. Their requirements are starting to form up a little bit, and we're seeing more and more interest from the Europeans on, okay, so what would a collaborative combat aircraft look like? And then for the propulsion side, you know, what would you need to power them? I think they're still working through, like, how big should it be, how low cost should it be, if you want to put survivability, how stealthy should it be? But that's another trend we're seeing that I think is going to gain legs over the next couple of years.
But your ability to accelerate that design cycle through the combination of AI, the additive manufacturing, your teams, and just the iterations they are getting through designing these smaller engines will allow you then to be able to respond more effectively to that marketplace.
Yeah, that's 100% true. And I know you all had Otis on about a week and a half ago. So last year we announced we have a partnership with Kratos, and it's to develop small engines for, you know, these type of uncrewed applications. But it's to do exactly what you said. You know, they have a small agile team that's got some unique aspects of their design. They can run through that design cycle quickly. We have the ability to scale, to do further integration into larger platforms. So it's a real good partnership that allows us to get reps of building out engines that are cruise missile size, building out engines that are collaborative combat size. And then we've taken those learnings and we've actually applied those to our overall design process. So that now, instead of, you know, really the wrong way to do this would be to take how we build a high performance engine, all the steps we go through, and then remove the things that you don't need to do for a collaborative combat aircraft engine. It's the wrong way to do it. We've started at the bottom and said, we're only going to add in the things that we need to give it enough performance at the right cost so that we can have affordable mass for our folks that want CCAs.
So I'm really curious, what sort of transferability do you have between those teams for the engineers that are on the small engine teams versus the engineers who are on the NGAP team or other, you know, F-110 team? What kind of cross flow do you have in terms of sharing knowledge processes and actually even sharing talent?
Yeah, that's actually a great question. So the small engines team, at least the GE one, they came for the big engine, you know, high performance engine side of the house, so they understand all of those processes really well. And the teams really do flow information back and forth. So that team has stood up a new process that's much more streamlined, much more agile. They've fed back to our existing process. You know, here's some things that could potentially be improved. And then on the high performance engine side of the house, we call it a Hoshin Connery, but we have a major improvement effort going on right now to dramatically decrease the amount of time it takes us to design, develop, and demonstrate an engine. And so their target is to cut it by 50%. And they're taking some of the learnings that we've gotten from the small engine team, and then they're taking other learnings from other parts of the business to go forward on that. And that's part of enhancing our ability to be able to deliver for our customers.
Wow.
You mentioned Otis before. Is that Otis Winkler?
Winkler, yes, sir.
I never liked that guy.
Yeah, nobody
Never
does.
liked
That's
that guy.
okay.
He's super smart, though.
Yeah, small world. He was actually in college classmate of mine at ROTC.
Is that right? It is a small world.
Yes, sir.
You know? So we've talked a lot about engines, and we talked a little bit about generational platforms in the Air Force. We're in the sometimes glacial move to do a generational reset with the slow purchase of other aircraft. But with just a little bit of luck, this administration that's coming in is going to start ramping that up. Obviously, that affects the airframe industry, but how does it affect the propulsion industry?
Yeah, so it affects us similarly. So, you know, we're seeing increased demand in our legacy engines, our existing engines today, but we're also seeing a little bit more interest in these next generation developments that we've talked about. So the way it really affects us, particularly in Edison Works, is we have the capacity, and actually across all of GE Aerospace, we have the capacity, we have the capability to deliver on both the existing engines that people want to produce and the next generation engines. The challenge is we have to have that consistent demand signal. And we're getting it now in certain areas, but we're not getting it in other areas.
So there's been talk, and I won't say it was Otis or anybody else, there's been talk that it will be challenging to actually field the F-47 and the F/A-XX, the Navy at the same time. And one of the challenges in that is propulsion. You don't see that being a challenge?
We really don't. Yeah, so that's one that I wholesale reject. So it's that both the Air Force and the Navy have come out publicly and said that we, GE Aerospace and Pratt & Whitney, are competing for the F-47 and for the F/A-XX, and we're also performing on the next generation adaptive propulsion program. So that's about all I can say about that part of it, other than to say that we have been competing. So it's not that there's a concern about can we. We've already been doing it. So we've been competing on these programs for years. We have the teams in place. We've got the supply chain ramping up. So we just need the go signal and we're ready to go.
But Doogie, I'm going to push back because I think the government has been a very poor customer and a very poor partner when it comes to industry across the entire defense industry, whether or not that's avionics, sensors, systems, platforms, aircraft, weapons, or engines, because the demand signal has been so capricious that really challenges companies' abilities to be able to smooth their workflow, order raw materials, do the long lead items, care for their subs. And that's a really fragile piece. And I know that GE you've been investing in your sub-tier suppliers.
Yeah.
And so that's, I think, something that you've done and taken on your own, really, to ensure that you've got a healthy ecosystem. But I think that's something that the Defense Department really needs to consider, is that if you want a healthy ecosystem within your defense industrial base, you have to buy. And you have to buy in volume, and you have to buy consistently, because that's the only way that you're going to get any of the companies, whether or not those are the sub-tier suppliers or the primes and the heritage companies, or frankly even your venture capitalists, to do the investments on their own. Because if they don't see production and procurement at the end of that, they're really not going to see the benefits of the investments that they make. And so if you want those investments on the company side, you have to be able to buy.
Yeah, I appreciate you bringing that up. So earlier this year, GE announced that they're investing $1 billion into our manufacturing base and production. Some of that's within the company, some of that's within the supply base. About 200 million of that is on the defense side. And then in addition to that, things we've been working on to try to smooth this up and down, because we have started a program, gone on pause, don't know what's going, start again. So things that we've been doing is we've been pursuing long-term supplier agreements where we'll essentially commit to a supplier that, whether demand goes away or not at our level, we're going to buy X amount of parts from you over the next several years.
And you can do that partly because you're commercial based, right?
Yes, there's part of that, but we are accepting risk, because if the program goes away, then those are parts that aren't going to be usable on the program, so we're going to lose money when we do that. And the other thing we've done is we've self-invested to keep our teams together and to keep our suppliers going in several cases. So just this past year, and this is not IRAD investment, this is actually pure investment of profit from the company, we've invested about $100 million into keeping our teams that are working some of these programs together. And so that's our commitment to be a good partner with the Defense Department. And so yeah, we're looking for that go signal so we can keep going.
I'm going to say that's incredible, because for smaller companies that don't have that kind of cash on hand, they can't make that kind of investment on risk, right? They're going to have to lay people off. They're going to have to move engineers and folks to other programs, because they got to keep them fed, right? They have to ensure that they maintain good business practices. And so really kudos to you for making that kind of investment.
I appreciate that.
Yeah, so this is the supply chain side, which took a torpedo in the water with COVID, and many companies are just now starting to recover from that. But you guys are going in and actually helping out your subs to bring parts forward, which is crazy good. The challenge with having Type A talent, really extraordinary talent, is one that I understand.
Right.
You have to actually challenge that Type A talent with Type A challenges. Talk about your workforce and the challenges that you're facing with regard to sustaining the talent pool that you need.
Yeah, I appreciate the question there. So, building a modern fighter jet engine is a very complicated process. People don't realize, and it's same for commercial engines, by the way, as well. But people don't realize that the components that operate in, particularly like in the hot sections of that engine, they're filled with cooling holes. They have to survive thousands of degrees. So it's a very unique set of talent that it takes to be able to build that, and then on supply chain to design that, and on the supply chain side to actually build it. But then it gets even more complicated when you get into like the Edison Works world. So like most organizations that have Works somewhere in their title, we work on survivable platforms, be they stealthy. And so when you're integrating low observable technologies with engine, high performance engine technologies into these extremely complex platforms, that's not a skill set that exists anywhere. You can't just go pull somebody out of college and they have that skill set. So we take a very deliberate approach to how we build that talent. And so at GE Aerospace, we're very blessed that we've got a huge pool of really talented engineers to pull from. And so what we do is we pull them into our Edison Works type of activities. We set them next to a subject matter expert who's been working it for years, because in a lot of cases, the only way to learn it is to actually be doing it. Unfortunately, this is often in cold, dark rooms with no windows in the back, but But they learn over time, and then we try to keep that pipeline going. So they've then become the subject matter experts that train the next generation. And there are times where you have a critical resource that's really hard to replace, and you have to come up with a special way to either go get somebody or train somebody up quickly. But it really is a real challenge. And so that's the challenge of building the talent. The second challenge that comes with it is how do you keep the talent? Because those are highly capable people that everybody wants at that point. And for us, it's really a combination of mission, I think, culture, and then there's this thirst for innovation amongst the folks. And what I mean by mission is our team, they really are proud of the fact that we're supporting America's warfighters and our allied warfighters. We wear our next generation program patches on our shoulder, just like the military wears their unit patches going around. And I'm not kidding, you walk around Evendale, you walk around our other facilities, they'll be wearing their patches, their jackets, because they're really proud of what we do to support the warfighters. So there's a sense of mission that really drives people to want to keep working in this type of environment. On the culture side, I mentioned that we have people that work in cold, dark rooms in the back in a vault with a door on it, and often they can't tell their neighbor what they're working on, so you lose a little bit of that camaraderie. So we have some very deliberate efforts going on. We call it our How We Work campaign, where we're trying to make that environment as positive as we can. So it's refreshing the tool sets that they use. A lot of our young engineers, they're coming out, they've been working with AI, large language models, the modern model-based tool sets. And a lot of the stuff that we have in the back has not been modernized in years. So we've also invested, it's well over $100 million in modernizing our model-based engineering tools and things like that for them. And then I mentioned the thirst for innovation. If you want to work on at least what I think are the coolest activities that are going on anywhere in GE Aerospace, the most innovative activities, a lot of that's going on here. You get to work on ramjets and hypersonics, the small engines we talked about, and then the highest performance combat engines that have ever existed on the planet. So I think those three combine to help us keep the talent in.
People like doing hard things, and it sounds like you're really giving them the challenge, or giving them the purpose, the why behind doing those hard things. But you mentioned the expertise that you're cultivating. Can you talk a little bit about how long it takes to take an engineer who's just newly graduated from college and make them useful, how long it takes to build an expert? Because this on-the-job training, you certainly can't have someone who is inexperienced inadvertently make mistakes. How do you build them up, provide those checks, and teach them so that they can become the expert? And how long does that take?
Yeah, it really takes a long time. So you can take a really talented engineer, bring them into kind of a subset of the design process, and they can learn very quickly what's going on in that part of the process. But to build up an expert who really understands the full integration, how do low observable properties integrate into
like
an engine that's running
right?
at 1,000, it's decade plus.
Decade plus.
And so we have folks that have been working in this area for 30 plus years, and they really are national experts, and we pull
national
as much
treasures,
really.
Really.
Treasures, and we pull as much knowledge as we can out of them, and spread it around the team. But to build somebody with that sort of expertise really takes years.
Which I think then really reemphasizes the importance of the government being a good partner and actually buying, right? There's only so much that a company can subsist on research and development. You have to get into the production piece, because the manufacturing is the other element. You do the design at Edison Works, but you also have to design for manufacturing. And I think that's a really crucial component, because if you don't get to the point where you're going to be a procurement program, you lose that second step, and you risk losing not only the talent, but then also the knowledge of how to transition to manufacturing.
Doogie, does that force these episodic starts and stops, this unreliable customer, does that force you to take talent and move them from one program to another?
It absolutely does. In fact, we've been doing that over the last year and a half pretty aggressively. And what we're trying to do is preserve that talent within our organization somewhere as much as we can. Yeah. But there's times where you just can't do that. And again, it's highly qualified, talented people, and they're in demand. Our commercial side is growing, and they're growing fast. And if you can pull somebody like that, or that's something that they would love to do. The challenge for us, it's not just building the expertise, but when you think about it, they have to have clearances, and in a lot of cases, it's special access clearances. And if you're starting from scratch, that takes a long time to bring those folks in. So it's not like you can turn them off and then pull them back in and start back up again. It's once you stop or pause, it's a very long journey to get back up to the level of support that you had previously.
We talked a little bit about our adversaries' assets previously. If you go back to the first jet engine that was fielded in a fighter, and how that was pilfered by the Russians, and that gave them a leg up in their technology that they were actually able to sustain for a while. But our industry, and particularly General Electric, has been heads and tails above them for a while. Are they catching up now?
Yeah, so they are catching up, and we do know that they're certainly trying to borrow our technology still, like they have in the past. So as I stated up front, the Russians and the Chinese are the primary developers of fighter engines elsewhere on the market. For many years, the Chinese had sort of relied on the Russian propulsion systems, but they've started to build theirs indigenously. And they've got a lot of people, a lot of smart engineers too. They're working fast, and they have a demand because they're building many jets. At a high level, our reliability tends to be still an order of magnitude better than theirs. So a lot of our engines, just general numbers, you can run for thousands of hours before you have to go through an overhaul activity, whereas theirs is probably hundreds. But they're getting better, and we're seeing them get better. And so that's just why it's that much more important that we take this next generational leap to make sure that we maintain that advantage that we have.
And JB, you and I both flew combat, and so we understood at the time that our engines were an asymmetric advantage for us, right? Because going against the Russians or going against other adversaries, we knew that we had reliable aircraft that could outperform what the adversary was doing, in many cases because their engines were not nearly as reliable. And so I think forsaking that asymmetric advantage, especially when we talk about next generation adaptive propulsion and F-47 and what's going to happen with the B-21, we really need to be conscientious to ensure that we are still investing within the industrial base to maintain that advantage and stay ahead of the PLA, because the Chinese, they are not stupid, and they have a second mover advantage because of all the industrial espionage that they've done and the mandatory tech transfer that they've imposed upon U.S. companies that manufacture within China. And so what they do with their military civil fusion is transfer the knowledge of manufacturing and material sciences to give them an advantage. So we need to ensure that we're continuing to invest to maintain that advantage for a warfighter, that lethality.
Yeah, I completely agree. So we talked earlier about the 40th anniversary of the F-110 engine. God bless it. I love that motor. But 35 years ago, GE was a major player in the F-22 engine, which is the YF-120. Now we're talking about NGAP. Could you talk a little bit about what attributes the Air Force is seeking and their willingness to actually buy those assets once you develop them?
Sure. So I won't talk about NGAP requirements specifically because those are sensitive, but I could talk kind of holistically about where we're going. So if you go back to the F-22, F-35 days, the real focus there was speed and maneuverability, right? And so there were other requirements, but that's really what we were looking for at the time. If you look at what the next generation of platforms is looking for, they still want that speed and maneuverability, but we certainly want range. And we also want the ability to pull additional power off of the engine and the cooling off the engine, because there's so many sensors and other systems operating on these complex aircraft now that drives a big part of the requirement. One thing I can say about NGAP, and again, kudos to the program team for pushing this, but a cornerstone of their program is model-based design and model-based engineering. And so they have put requirements in the program that have really encouraged us to go out and up our game when it comes to model-based enterprise in general and model-based design, and the ability to even flow that all the way down to our supply chain. And so we actually just earlier this year completed our first ever fully digital critical design review on our XA102 program. We put out a press release on that. But that was if you've ever been through a critical design review, they're painful, but that's usually hundreds and hundreds of PowerPoint charts, and going through this wasn't a single PowerPoint chart. We literally just put the digital model up there. You go in, you click on an attribute, it can tell you what the heritage is of the requirements, how we're going to verify them, and all that. So a huge leap in technology that they've really pushed us to do.
Did that accelerate your timeline?
It actually, be perfectly honest, it slowed us down a little bit this time because we were learning it.
Okay.
It will accelerate us in the future, right? And now what it will accelerate is anytime we need to do a design iteration, you're not generating a bunch of drawings, you're printing them out, passing them to someone. You can actually do that digitally, and even if you're pretty far down the process, you can make an iteration and it feeds all the way back through the model. So it's a dramatic enabler, and it's a huge change in the way we've done business for many, many years.
Yeah. How deep did you have to go into the supply chain to make that happen?
That's a great question, because in some cases, parts of the supply chain can't ingest models yet. They just don't have that capability. And especially if it's a small mom and pop shop that generates a couple of parts here and there, they're not going to make a multi-million-dollar investment, in a system that will be able to ingest a model. So we have a few suppliers that we're working with specifically to demonstrate that, hey, we can flow a model to them, they can generate a part, and then they can feed it back to us.
Excellent.
I'm one of those guys that loves to go like this and stand the airplane on its tail, relying on the thrust that you create. It is just an incredible, dominant combat capability that you feel when you get in the jet. But if you can't get back home from the fight, or if you can't get to the fight because of the range, that's its own really critical aspect. We're looking at a fight in China, the second island chain, 1,700 miles away from Taiwan. That's not engagement time, it's a 5-hour round trip. You got to get to it, and you got to be able to get back to the tankers that will allow you to get home. Could you talk about that attribute and how GE is working that in the equation?
Yeah, so at a high level, the most important thing when it comes to a range of your platform is the outer mold line. The second most important thing is the propulsion system. So the propulsion system, in our mind, your engine equals range. So you think about the adaptive cycle engine, for instance, that's where you get this additional range. It's because you've got such better fuel efficiency that you can take the same engine, but you can deliver X% better range just by having this highly capable propulsion system in there. So that's the heart and soul of what we're trying to provide. I'll deviate really quickly to hypersonics. There's a technology in hypersonics called rotating detonation, which allows you to have a smaller combustion chamber, but it basically equals range for our warfighters too when it comes to long-range weapons or potentially long-range aircraft someday. So range plays into everything. Our small engines that we're putting for CCAs, range is a critical factor because they're meant to operate in that AOR. And so as we're designing up the capability, we need to make sure that they're able to perform at least as good as or better than the existing engines out there. So that's a requirement that's front and center in pretty much everything we're doing now.
Well, and I think we shouldn't underestimate the impact that a more efficient engine in tactical aircraft will have across the entire theater, right? Because that gets down to how many tankers you need, where you can place them, how you can move fuel around the battle space and around the theater. So there are so many elements of goodness that come from changing the specific fuel consumption of the aircraft, allowing it to have greater range. That we shouldn't underestimate that, and that can provide benefits across the entire theater.
That's amazing. So we talked around a lot of things, but we're going to talk directly about the elephant in the room. We're right across the street from Capitol Hill, Congress, and right across the street from the Pentagon. If you had a message to convey to our senior leaders, both in Congress and in that beautiful building we call the Pentagon, what would it be?
Yeah, so it's a two-part message. And the first part, and I really mean this sincerely, the first part is thank you. Right? We've gotten a significant amount of support both on the Hill and in the Pentagon for continuing to pursue these sixth-generation platforms, next-generation propulsion opportunities. And without that, I think they probably would have died. And so the support that we've gotten from the Hill and from the Pentagon on those programs has been significant. So we really do appreciate that. So our first part of our message is thank you. The second part of the message is we're ready, let's go. Right? So there's still a few that are in purgatory. They're deciding whether we're going to go forward or not. The Defense Industrial Base is ready. GE Aerospace is ready. So the second part is we're ready, let's go. Just release the hounds, let us go.
Heather, anything to add?
I'm going to say bye.
Bye.
Right? I mean, we've talked about, and there's been my drumbeat, research and development is really crucial to be able to develop those advanced technologies, but it doesn't mean anything if you can't cross the valley of death and actually get into production. And JV, you and I have talked about the imbalance between the R&D accounts versus the procurement accounts. And right now, we are in a position where we've got industry is ready, and so we need to move into procurement, because that's the only way that is going to truly be able to field the capabilities, mature them in an operational setting, and provide the consistency that we need for industry to be able to manage not only their own workforce, their engineers, but frankly also their sub-tier suppliers. So if we're worried about the defense industrial base or the broader industrial base in America writ large, we really need to begin buying, and we do that through multi-year procurements. There's a statutory requirement to provide 10% savings for multi-year procurement. So we're in an administration that cares about getting the most bang for the buck. That means give us some multi-year procurements. And we got to go into buy.
So Heather and I have actually taken a pencil and we've scratched out the $28 billion surplus in RDT&E, and we've moved it over in our heads over into procurement. You guys do IRAD. You pay for a lot of it. How would cuts in RDT&E affect your ability to generate the next propulsion platform?
Yeah, so they are negatively impactful, and it's a significant negative impact because a lot of that initial development funding comes through the RDT&E lines. And when you think about all the trades people are making, as we talked about at the very beginning, propulsion isn't the top of mind for a lot of folks. It is for a subset. The propulsion directorate does a great job of advocating for themselves. There's some key users that advocate for it, but if you don't realize that this is a key requirement that you have to invest in early, and that's on the R&D side, it's not going to get the love it needs to be available when we need it down the road.
Well, and I think that's why JV and I have consistently advocated, Mitchell writ large have consistently advocated for not just a rebalance, but a rebalance that's smart, taking into account really where those technologies are, where they are in terms of their ability to move into and transition into production, and sort of what's that time frame. Because although we do need to have that element of what's looking out at 2050, 2040, in reality, we also need to really be conscientious about ensuring that we make the investments that we can feel within the next 5 to 10 years. And I think that's where NGAP is squarely set.
Yeah, and I guess another final point on that is that some of these technologies also, they're not technologies that the broader commercial enterprise is going to be investing in. There's not a demand for LO aircraft with high-performing engines on the commercial market right now. So if you don't invest using your RDT&E funds, it's not going to come from some other part of the market. So that's another reason it's so critical to have at least some focused investment in these things.
Yeah, because as much as we love the commercial in the civil space, there's not always that transition. There are some pieces that are very unique just simply to the defense arena, and we have to be sensitive to that.
I don't know if you put an adapted engine on a 767 and put me in the nose, I'd do my best to stand it on its tail.
I believe that.
So I love the commentary. We put almost $5 billion into AETP. We delivered, GE delivered 4 miracles in that process, and the only thing we were missing was the purchase. And we've got to move down that path. Ladies and gentlemen, we've come to the end of this Aerospace Nation. Doogie and Heather, it has been an absolute joy to be with you. I've loved the discussion. Thanks for taking time to speak with us today, Doogie, and you're bringing your staff in here. And for you all, ladies and gentlemen, thanks for being with us. From all of us at the Mitchell Institute, have a great air and space power kind of day.